you'll want to watch the videos. The first one, I apologize that it's a longer video, but I assume you will know how you can you know, figure out how to pause it on your own and stuff like that. Okay. Okay, so let's go ahead and I will share my screen and just give you a bit of a spiel on this, and then I will go to, you know, going over your programs with you. Okay, so share screen. Okay, so as I mentioned, you know, trees are a hierarchical data structure, where basically you have some node at the top, and then it which we call the root, and the root has children. Each it has leaves, it has descendants. The vocabulary, as you'll find out, is very fluid. Whatever one person likes, another person might like differently, but regardless, you have some node at the top, and you can have any number of, and any node at the top can have any number of children, okay? The key there, for right now, for our class, and for the majority of your program, you will be focusing specifically on binary trees, which means that each node here can have at most 2 children, which we specify as the left child and the right child. Sometimes you only have 1 child, specified by that X over there. A lot of times it isn't explicitly drawn, where that X isn't explicitly drawn, and you just leave it blank. But sometimes it's useful to draw that X to let you know where space is. And again, you might have no children. Nodes that have no children are called the leaves, and the node at the top is called the root. Now, you may recognize this as kind of the way a tree works, only in reverse, right? Like a real biological tree, right? Where in a real tree, a biological tree, you would expect the leaves to be at the top of at the very top, and the root to be at the bottom. So just chalk this up to the fact that computer scientists don't go outside that much, I guess. Or maybe it's one of those weird zero-grav hydroponics things. I don't know. But the root is at the top. It's called the root because it's the most important. Okay. And everything grows out of it. So with that said, let's see. So with that said, we're going to be dealing with binary trees. But again, we might deal with, in theory, there are trees like this. There are, you know, n-ary trees, where basically you could have up to, like, here's a trinary tree, it has 3 children. There's also other weird trees like 2-3 trees, where each, you know, node might create, I'm sorry, where each thing might contain multiple values. You know, so that one might contain X and Y, and this contains A, and this contains, sorry. I have to do this with my fingers. There's all sorts of trees, but right now we're dealing with specifically 2 types of trees. Both are binary. So you've got yourself the binary tree, okay? The binary tree. And that just kind of refers to the fact that these things can have only 2 nodes, okay? And then we also have ourselves what, geez. Okay. We also have binary search trees. And that's where probably you learned a lot of stuff in 1166 about. Binary search trees are what we care about, what we typically use for trees for. Binary trees are nothing more than, by themselves, are nothing more than graphs with a very interesting property, with a few very interesting property. All trees are graphs. So But binary search trees implies that there's an order, that the things are sorted, okay? So a binary search tree might look like this, okay? Might look like this, 7 as the root, and then we've got, you've got 5, 10, and then we've got 6, 2, 15, and 8. So binary search trees have this property that for any node, it's a binary search tree if and only if all the nodes to left are less, and all the values that are greater are to the right. Left less, right greater. Okay. Assume for the sake of argument that we don't have duplicates right now. You can handle
If you
duplicates
go.
very easily, but assume no duplicates. Okay, and then so that's the first thing. The second thing is that the left side and the right side are both binary search trees. It's a recursive property, right? So basically you have to be a binary search tree. You're a binary search tree only if the things to the left and right are less and greater respectively, and that your left tree and your right tree are both binary search trees, which means that they sort themselves out. And you'll see that's the case here, that everything to the left of 7 is less than 7, everything to the right of 7 is greater than 7. And for 5, that's true as well. Okay. So the big thing about trees also to keep in mind is that you can have multiple children, but you can have only one parent. Each node can have multiple descendants, multiple children, but it only ever has one parent, one node directly above it. Okay. So, any questions so far on that? This sounds familiar to everybody? Okay. So let's go ahead and talk about the stuff that you're probably interested in, which is what do you need to know for the test, which will probably be in like 3-ish weeks, I would think. What do you need to know about binary search trees? Because binary search trees are going to be the focus of the exam. You'll need to know things like if I wanted to add well, let's go back to this. If I wanted to add the number 12 to this binary search tree, how would I go about doing that? And the answer is that if you wanted to add 12 to this tree, you'd compare it to the root. 12 is greater than 7, so you go to the right. 12 is greater than 10, so you go to the right of that. And then 12 is less than 15, so you go to the left of that, and that's an empty space. So we're going to go simply and put that, and we're going to put the 12 there. As well as knowing how to delete things from this, which is a bit more of a complicated operation. But say you wanted to delete 7, you can't just simply shuffle things around. It's a bit hard to shuffle things around. Instead, what we do is that we need to replace it with something that also works as the root. As it turns out, 6 really works as the root. So what we end up doing is that we end up replacing that 7 with 6. And there's a very easy algorithm that we use to replace that. I've once been asked that as a mock interview question. It's not exactly a hard algorithm to do. All right, so am I sharing my whole screen? Yes, I am. So what do we need to do for the homework? For the homework, you've got, for this one, 3 files. So you've got the index tree over here, and you've got index node, index tree, recording from file example. The index node, the node I've kept separate from the tree just because. The example is not anything you need to do with the homework. What that is that shows you how to read a file, because when I initially wrote this assignment, we didn't necessarily teach that in 1068 because the curriculum was a bit different. So we wouldn't necessarily have time to go over file reading. So hopefully you know how to do file reading, but if you don't, we've got a handy dandy example file right here. Okay. Okay, give me a second. Apparently it doesn't want to do that. So let's go ahead and desktop. Index node, index tree. Reading file from this. And I'll just briefly go over this and then I'll help you with wherever you are. So let's go ahead. Okay. Drag these all into here. Refactor. Okay. So first oh yeah, I might as well. So this file, is going to be, so yes, let me show you this because you probably haven't had to read a file before. pg100.txt. So the goal of this assignment is to do an index is to create basically the index that would create come at the back of a book. But we're doing it for every word in a file. Okay. So basically you're saying, okay, this file occurs here, 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 and here. It occurs and rather than pages, we're using line numbers. So this word occurs on line 7, line 8, line 15, line 52. And the file we're using for that is the complete works of William Shakespeare. That's what PG 100 is. It's Project Gutenberg 100. Now, where do we put this in the file? So one of the things you got to know is where we put this. If you're working in Eclipse or in IntelliJ, follow these directions. If you're working in VS Code or Vim, you'll figure it out on your own. It's probably not nearly as hard. But basically, if you're working in something that has an SRC folder, you do not put the file in the SRC folder. You take the PG100, the file we want to read, and we put it on the top level in order to read it. And see how it's outside the SRC folder? And that's basically where we can assume to read it. So if we and this is how you read it. It's very straightforward. You give it a file name and you say try, you do a try catch loop or try catch block. You try to do something, and if there's an error, don't crash. So try catch, what that does is you say, I'm going to try to do something which may crash the program. If it crashes, rather than crash, for instance, here I'm saying if you would crash due to a file not found exception, instead of crashing, just print out the error instead. So the way this works is that you honestly just use it with a scanner. The only difference, instead of doing system.in, you're doing new file name. Okay? And then you just simply say, while the scanner has another line to read, we read it. Okay? One thing to note is that while you're reading this file, you will probably get some, and once you get to the end, you're probably going to be like, uh-oh, this isn't working because I have a random the at the bottom of what's supposed to be in alphabetical order. So you might get to the end, you have, like some Z's as your last words, and then you have a random the at the end. That's fine. There's, this file has a random, like, beginning of the file random character just in between, just right before the that you can't see. That's what's going on. So don't be disheartened if you've got a random the at the end of your output. Okay. So also notice I've opened this up and it says the file size 5.5 megabytes exceeds the configured limit. Code Insight features are not available. Now, why this is important is if I go ahead and read, so I'm going to go ahead and run this example, which is going to read my and print out the entire file. Okay, you definitely want to make sure this works before you start coding anything for this project. And it's going and going, and there we go. And so I'm going to scroll up. And where's the rest of the file? The sonnets isn't the beginning. Oh, wait, is it? Oh, no, I've configured mine to print out the entire thing. Never mind, there we go. That's very less than useful of an example for you. I've configured mine to print out the entire, I've configured this to print out the entirety of the file. Is it the entirety of it? Do we have? Yes, yes it is. Okay. And your IDE may not be configured to do that. I specifically had to go into my settings and I had to change the buffer for the console. Notice that your console has a very specific thing. Override console buffer size. Your buffer has a 1 megabyte limit as to what it can keep in memory by default. So when you exceed that limit by printing out, say, an entire 5 megabyte file, it just simply throws away the top line. So if you print out your output and you're not able to see your entire output, that's why. Okay, so those are the headaches to come back to if you're having some issues with your output, which is that you probably aren't having any issues with your output. It's just your IDE. All right, so index node is your node. Okay, and what we're doing here is that we are basically creating a, oh, I see a question in chat. What we're doing here is that we're creating a binary search tree. It's gonna, and your code should look very similar to the example code I give you. In fact, this is actually a relatively easy project. The difficulty comes from A, file reading, and B, overcomplicating this. Okay, so here's your node. What does a node contain? Okay, a node in this homework contains, so a node, I'm gonna make it big, it contains the word that you're storing, say, the, okay? It contains a list of lines it occurred on. So it occurred on lines, say, 1 and 2 and 3 and 7 and 12. It occurs on a lot, okay? And then finally it has the number of occurrences. This file, basically, sorry, the way this works is that basically you're sorting on word. The tree sorts itself in alphabetical order. Now the question is, do you remember how to check how to put things in alphabetical order in Java? I mentioned it all the way back in week 2, and now here it's come back to us. And the answer is right here. Or rather, it's strings. The answer is we use compare to. We use compare to check if things are in alphabetical order. So this should become a lot more apparent and a lot cleaner once you once you watch the videos. Your goal, though, is that you need your add methods, yes, plural, because it's recursive. And you need your contains and delete method, and then finally a print index. You want to figure out the print index on your own and not use the one I use in my output. You will probably want to make your own helper method. So what you want to do is probably you'll want to use this you want to follow the same pattern for printing out the index. You have this method, which calls a private helper, private recursive method. Okay. So that's all my advice that I can give you before you actually watch the videos and get started on it. Okay, if you have more questions about it, please ask me on Wednesday, and I'll try to address them to the entire class. All right. Any other general questions before I start going around the room? All right, it doesn't look like there's any. So, no, I should be in person on Wednesday. I plan on being in person on Wednesday. I don't expect to hold another Zoom session until about April at that point. In April, I've got, I'm traveling for the eclipse, but that's about it. The only session I plan on holding over Zoom. If you're wondering why I'm traveling for the eclipse, it's so I can be in the path of Chotala. That's why. Also, by the way, like a week before, the price for like glasses, for like those really cheap pairs of glasses, that you use for solar glasses for viewing solar stuff, those get really expensive like the week of an eclipse based off of what happened 7 years ago. So I would acquire those now if you want them, or figure out a plan for viewing it in Philadelphia if you're not traveling for it. All right.